Hi everybody, tonight's lesson is all about linear programming. So the goals of this video are to maximize and minimize functions, which is just an introduction to linear programming. It's really the point. And then to solve real-life problems using linear programming. So linear programming is using a system of inequalities to find a maximum and minimum value of a provided function called the objective function. The constraints of the problem are used to draw the picture, and the shaded region is called the feasible region, which are the possible solutions. And then lastly, vertices are the points where the inequalities meet, and make sure you are very accurate because finding the correct vertices is the key to solving these problems. Without them, it's going to be tough. So those are the terms that you'll hear me use throughout the video. So if you want to look back, feel free to go ahead. So in number 1 and 2, we're going to find the maximum and minimum of the given objective function. The objective function is just this f of xy equals 3x plus 4y. We've seen function notation before, right? It's normally just f of x, but since our equation has, and our function has two variables, x and y, our function has two inputs. So the greatest thing about linear programming is that all we're doing is taking stuff that we already know how to do and putting it all in one problem. So first, we're going to graph the system of inequalities, which we just learned. So we're going to graph each inequality and see where they overlap. So this is what I mean. So our first function is x is greater than or equal to 0, which is a vertical line at 0. And then we know that we're going to have to shade to the right. I want you to shade very lightly though, or you could even wait. Our second function is y is greater than or equal to 0, which is a horizontal line at 0, and it's greater than, so I need to shade above. And then lastly, I have this x plus y is less than or equal to 8. So I'm going to solve for y so I can graph the function. So I have negative x plus 8. So my y-intercept is 8. 1, 2, 3, 4, 5, 6, 7, 8. Now, you can either use the slope or you could use the x and y intercepts, whatever you like to do. But the slope is down 1 over 1 all the way to the end. I plot all the points because I need to know exactly where my functions intersect, or my inequalities intersect. But now, y is less than this line, and if you were to plug in, I don't know, 1, 1, you would get 2 is less than 8, which is true. So I know I have to shade everything underneath this line. Now, it's kind of hard to tell, but hopefully you shaded lightly and you can tell where they overlap. So I'm going to erase everything I've shaded otherwise. And I'm just going to note that I shaded to the right, I shaded up, and I shaded down from each of these lines. I usually like to use arrows because in the end, I'm going to shade just the part that overlaps, which was just this triangle here. And then I have to make sure I know exactly where I have any two inequalities intersect because those are our vertices. Now, it's important though that yes, it's everywhere any two inequalities intersect, but it also has to outline our feasible region, that shaded region. So here, my vertices are 0, 0, 0, 8, and 8, 0. And I use those to solve the rest of the problem. So I'm going to rewrite my objective function down at the bottom so I can reference it really quickly without having to scroll. So I know I'm going to use f of xy equals 3x plus 4y. And now again, this is something we have seen before. All I need to do is evaluate my function for each of my vertices. So the first is f of 0, 0. So that means 3 times 0 plus 4 times 0, which is 0. Then I have f of 0, 8, which is 3 times 0, oops, plus 4 times 8. I'm just substituting in my values for x and y. And I get 32. And the last one is f of 8, 0. So that means x is 8, and now y is 0. 3 times 8 is 24, plus 0 is 24. So you have to evaluate your function at each one of your vertices, because that's how you're going to get your maximum and your minimum. And again, this is easy. The maximum, guess what, is just the biggest number, which is at 0, 8, and it's 32. Right? Biggest number goes with maximum. Makes sense. So my minimum, what do you think? Well, obviously the smaller number is 0, so it's at 0, 0. And we're done with that problem. So if you're not sure how I shaded this, I want you to rewind and try to watch one more time. I'm going to move on to number 2. This time my objective function is f of xy equals x plus 9y. Again, I'm trying to either maximize or minimize. So we've graphed plenty of inequalities, but I don't want you to freak out because we have this compound inequality. Remember, this is really like two separate inequalities. This is saying x is less than or equal to 5, and x is greater than or equal to 2, right? This is saying x has to be between 2 and 5. So I'm going to draw a vertical line at 2 and a vertical line at 5. And I know that I'm going to shade somewhere inside, but I'm not going to shade yet. I'm just going to draw arrows pointing the way that I'm going to shade eventually. I like to wait to the end, but you could shade now if you want, as long as you're careful and know exactly where your shading overlaps. The second compound inequality is saying y is less than or equal to 4 and y is greater than or equal to 1. Remember, this is saying y is greater, so we have to make sure we're writing these correctly. So I'm going to change my color here to, let's say, purple. Y is greater than or equal to 1 is a horizontal line at 1. So I'm done there. And then I'm going to draw a horizontal line at 4. So 2, 3, 4. And I can say, okay, I need to shade down from that line because it has to be less than 4, or greater, and greater than 1, I should say. Or we can also think that y has to be between 1 and 4. And also x has to be between 2 and 5. So if you move these arrows just down a little bit, where you're still going to shade to the right, we can kind of start to see where our area is going to be shaded. The last part, oh, that's kind of hard to see. I'm going to use the fuchsia instead. I need to graph my last inequality. So I'm going to solve for y first. I have 2y is less than or equal to negative 2x plus 14. Divide everything by 2. Y is less than or equal to negative x plus 7. So I'm going to go to my y-intercept of 7. So 1, 2, 3, 4, 5, 6, 7. And I'm going to go down 1 over 1 until I'm done graphing. And I like to mark every point because it's very important to know exactly where your graph goes. Then this says y is less than this line, so that means I need to shade below it. Or maybe you'd want to choose a test point. We could choose 0, 0. That means 0 is less than or equal to 14, which is true. So I know I have to shade below. But you have to be extra careful to keep in mind what the other constraints were and where you're shading. And where you are shading is this 5-sided figure right here. If you are not sure, I would like you to rewind and watch again. And I'm going to carefully mark everywhere I have any two lines intersecting. But remember, it only matters if they're outlining our feasible region. Like this one here, I don't really care about it because it's not touching my shaded region. Same with this one. So just make sure you're paying attention to that. So I would like everybody to pause, and I want you guys to write out the vertices. So I want you to look at your graph and write down those vertices. And I really, 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 really want you to pause. Did you get the same vertices I got? I hope so. Check your answers. So I also wrote down the function that we're trying to maximize. So now we're going to pause again because I need you to know how to do this problem when we get to class. So I want you to figure out the maximum and the minimum of our objective function by evaluating it for each of these vertices, just like we did in the problem over here. Ready, set, pause. All right, so hopefully your work looks the same as mine. And you got that the maximum is 39, which is when x is 3 and y is 4. And you got that the minimum is 11 when x is 2 and y is 1. So if you didn't, I would like you to pause again and make sure that you correct your work. And hopefully you'll rewind and rewatch so you're prepared when we get to class tomorrow to replicate this problem. So the last problem, we're just going to start this one together. And we can see how linear programming can really help us in a real life situation. So Diane and Esther run a cake making business. They sell cakes, birthday cakes, and wedding cakes. It takes 2 hours for baking and initial prep for each birthday cake and 5 hours for each wedding cake. And I'm going to change colors and I'll show you why in a second. Then they decorate for 2 hours on each birthday cake and 10 hours on each wedding cake. They profit $150 for each birthday cake and $700 for each wedding cake. And then between the two of them, they want to work no more than 20 hours on initial prep and 30 hours on decorating each week. How many of each type of cake should they sell to maximize profit? So, the reason I changed colors is because I wanted to keep my units the same and what they were talking about and wanted to group it by topic. So, the first thing we need to do is outline our variables. So let's have x be the number of birthday cakes and y be the number of wedding cakes. So your objective function is what you're trying to maximize or minimize, depending on the problem. So what do they want you to maximize? Well, it says to maximize profit. So your objective function, we'll label it f of xy since x and y are our variables, is what we want to maximize. Well, it is profit. So I underline those in this light blue. They profit $150 per wedding cake plus $700 for each wedding cake. So then I get to be done with that information. So now I'm even going to erase the blue so we don't try to use it again. And then we have constraints. Well, they give us a bunch of information and you're going to have to write these inequalities yourself. So it's really important that you can group information. So I underlined in black our first piece of information. It says 2 hours for baking initial prep for each birthday cake. So they prep for 2 hours for each birthday cake and then 5 hours for each wedding cake. And then it says they don't want to work any more than 20 hours. And I don't blame them. So this is the amount of hours that they work. That has to be less than or equal to 20. So then we're done with that information. It all has to match to go in the same inequality. Then I underline in blue every time I see decorating. So all of these pieces of information have to do with decorating. It says 2 hours per birthday cake and 10 hours per wedding cake. And then it says they only want to work less than or equal to 30 hours, right? They don't want to work more than 30 hours because that's a lot of hours. And then the last one is that x would be greater than or equal to 0, and so would y. They have to be positive because we can't make negative amounts of wedding cake. So we just draw those as, create those as constraints. So what I want you to do is I would like you to graph these constraints and see if you can come up with the vertices. I know you can because you were paying attention this whole video and you might even try again to rewind and rewatch. So remember you need to solve for y, so you'll have y is less than something up for both of these to graph, and then you can graph these two lines. Find the vertices, and once you do all the math, you'll be able to tell me the minimum and the maximum. So do your very, very best, and I'll see you tomorrow.